Hello everyone. In this particular session, I'm going to show how to use EpiData Analysis to perform some inferential statistics. So let's open our data set. Let's read mdrtb new.rec with all the recorded data. Let me also open my editor. Fine. So let's go on. We go down. Yes. So let's look at some of the inferential statistics. Some of them we have already seen. For example, calculating confidence interval around a mean and a proportion we had already seen yesterday. Let me make the variables visible. Let me sort of do a quick recap. For example, freak sex, okay, percentage, column percentage, and with an option CI, I have already got the 95% confidence interval around a proportion. So this is going to be similar for any proportion. Okay. Similarly, the command means age actually gave the confidence interval around the mean as well. So if you have a continuous variable and want to calculate mean and confidence interval around the mean, the command is means. Okay, so let's move ahead, and there are some exercises here. Let's do that and bring out additional concepts. Okay, so it asks, there is a question, is there a difference in mean age of diabetes mellitus and non-DM patients? Okay, and is the difference statistically significant? So this is what we have to look for now. Okay, let me clear the screen and start. So the command is means. We want to look at means age. The command to look at a particular breakup by a variable. Okay, so if you want to look at by diabetes and non-diabetes patient, the command, the option is by, okay, equals the name of the variable, which is DM. Is this clear? The syntax, it means the command, the name of the variable, and you want that disaggregated by diabetes status. Okay, let's run this. Okay, so do you see the output here? So we have mean age among those with diabetes and among those who don't have diabetes. Okay, and you can see among those with diabetes the mean age is 48.78 years, and among those who don't have diabetes it is 41.47 years. Okay, and medians also are almost similar to mean. So already you can begin to see certain things. One is the mean and median are almost same, 48.78, 48. Similarly 41.47 and 42. So this indicates, this is one of the indications that the distribution of age could be normal. Okay, so this is one of the things you have to keep in mind, because there are certain assumptions that you have to fulfill before you use a t-test, and one of the assumptions is that the distribution is normal. Okay, fine. So now we see there is a difference, 48 and 41. The question we are asking is this difference statistically significant? And the test that we do in comparison of two means of two different groups is a t-test. T-test, and the option here is, all you have to do is option T. Okay, so let's do this and see what happens. Great. So you have this difference, and then you have a analysis of variance in fact here, and then the p-value is 0.002. So the the probability that this difference is just by chance is very low, less than 0.001. So we think this difference is statistically significant. Is this clear, everyone? So this is a t-test. In fact, what it is doing here is a ANOVA, analysis of variance. Analysis of variance is usually used when you have more than two groups, when you want to compare means of more than two groups. But there is no harm in using for two groups as well. When you use it for two groups, ANOVA and t-test is almost the same. Okay, so this can be used as a t-test. Now, before we use parametric tests like t-test or ANOVA, there are certain assumptions. I was telling you that one of the assumptions is about normality of distribution. There are various ways to look at normality of distribution, and one of the ways is looking at mean and median, and if they are similar, then that is one indication that this distribution is normal. The other way is to look at coefficient of variation. We told you in my earlier lecture that divide standard deviation by the mean and see if that is less than 50%, then also you can say this is mostly normally distributed. So for example, here I can do the calculation using a command question mark. Okay, I can say 9.1 divided by 48.78, and then I get 0.18, which is about 18%. So it is normally, this is also another indication to say it is normally distributed. The other way of looking is to look at visually. So draw a histogram of that variable and see whether it looks normal. Okay, it sort of looks normal. Is this clear? So these are some of the ways of looking for normality of distribution. The other important assumption is that there is homogeneity of variance between the two groups. So you should look at the variance in the two groups. So in the first group, that is diabetes group, 82 is the variance, whereas in the non-diabetes group, 172. Clearly there seems to be a difference in variance. So it is not homogeneous. The homogeneity of variance is probably not satisfying here. But that can be confirmed here in this table. At the bottom you have a test for homogeneity of variance, which is called as Bartlett's test for homogeneity of variance. And here if the p-value is less than 0.05, then you can be sure that there is the homogeneity of variance assumption is violated. Okay, it is not getting fulfilled. So that is another assumption for doing a parametric test. So because the homogeneity of variance is not getting fulfilled here, I'm going to show as an example a non-parametric test. Okay, in this case in EpiData we have a non-parametric test called Kruskal values, and the command is k-values, Kruskal values. Is this clear? Okay, so because there is no fulfillment of the assumption of homogeneity of variance, I'm going to try and use a non-parametric test, which is Kruskal values. The syntax is simple. All you have to do is k-values, that's the command for age, by dm. Let's run this, and you see the p-value is 0.002, which is the same as what it was earlier. Okay, let me show both of them together. Okay, so Kruskal values, here it's 0.002, here also it is 0.002. In other words, t-test is quite a robust test. Even if one of the assumptions are not fulfilled, many a times it works very well. Is that clear? Okay, fine. So let's move on. So we have answered this question. So in this you have learned, if you have a situation where you want to do a unpaired t-test, okay, can see the difference between means of two independent groups and see if it is statistically significant or not. So we also have to demonstrate one more, which is a situation of paired t-test. That means a pre-post intervention. So you have a mean at baseline, you do some intervention, and there is a change in mean after the intervention. That means every study subject has a pair of values. So how do you do a pair t-test in this case? Let's look for a variable which we can use here. So for example, we have a variable called weight at diagnosis and weight at the end of treatment. We can see whether there is a difference in means between these two. Okay, is there a significant change in weight after the treatment? Is this clear? So this is a situation where you want to use a paired t-test. So there is no direct way of doing a paired t-test in EpiData. We have a workaround for it, and I'm going to explain that. The first thing is you have to calculate a weight difference. So let me call this new variable weight difference, which is equal to weight at the end of treatment minus weight diagnosis. Is this clear? So I'm going to generate a new variable which will calculate the difference in weight from diagnosis to end of treatment. Okay, let me run this. So I'm getting an error here. Why am I getting an error? It says data type mismatch, because the weight is in decimals. So if you deduct one by the other, then you will also get a decimal. So it has to be a float variable. So let me run this now, and then it appears. Okay, now we have weight difference, and all we have to do now is simple means weight difference option T. So this will do a t-test assuming that the difference is 0. So let me run this. Okay, can you see this? This is student's t-test for mean equals 0. So it's assuming null as 0 and then doing. And there is a change of 3.38 kgs. So which is significant. Is this clear? How to do a paired t-test? Okay. So let's move on and look at other things. So one of our objectives was to look at factors associated with unsuccessful treatment outcome, isn't it? So let's try one by one. Is age associated with treatment outcome? Okay, that is the question. So there are various ways of looking at it. One way is to look at mean age among those who had a successful treatment outcome and compare that with the mean age of those who had a unsuccessful treatment outcome. So how to look at that? Means age, simple, by equals outcome 2. We have a new variable, isn't it? So I'm going to run this. So I have 42 years is the mean age among successful treatment outcome, and 46. So those who had an unsuccessful treatment outcome were relatively older as compared to those who had a successful treatment outcome. Now I want to see if this is statistically significant, this difference in mean age. So I run, and then I get a p-value of 0.03. So since this is less than 0.05, we will consider this as statistically significant. Okay, so age appears to be related to successful or unsuccessful treatment outcome. Is this clear? The other option is we could divide the age group into certain categories and then look at it categorically. Okay, I'll show you that as an example. Let's take another example, okay, for categorical. So this is sex associated with treatment outcome? Is sex associated with treatment outcome? Clear? So we want to see whether the proportion of unsuccessful treatment outcome among males is any different from that in females. Okay, so that is what we want to achieve. Now here we want to do a cross tabulation, isn't it? Because we are looking at two categorical variables. So here we learn a new command, that is tables. You see, I think we showed you about tables in the last session as well, when we were trying to verify whether the recoding happened right or not. Okay, so let's look at now. We'll use the same one, tables. So in tables there are row headings as well as column headings. Okay, and conventionally outcomes are presented as column headings and exposures as row headings. And in the syntax, after the command tables, the first variable you put will come as column heading and the second variable you put will come as row heading. So since our outcome variable is outcome 2, I'm going to put that first and then sex as the exposure variable. Is this clear, everyone? So after the command tables, the first variable, whichever you put, will come out as a column variable and the second one will come out as a row variable, and that is how we want to set it up. So let me press F8. Okay, so now we have the numbers in cross tabulation. I wonder we have the percentages as well. Now what percentage do we want? A row percentage or a column percentage? This is often the question. And depending on how you want to make sense of the data, you can choose. Now here I want to see what is the proportion of unsuccessful outcome among males as compared to females. So I will go here with the row percentage. The formula for row percentage is option R. You remember for column percentage it is option C. So here for row percentage it's option R. Let me run this. Do you see this? The proportion with unsuccessful treatment outcome among females is 20%, while that among males is 42%. Clear? So males appear to have a higher rate of unsuccessful outcome. Now the question is this difference statistically significant? Okay, you have a difference in proportions. Is that difference in proportions statistically significant? How do you do that? Again, option T. Option T. Now in this case, you will get a EpiData Analysis will run a chi-square test for you. Okay, which is the right test for testing difference between proportions. So I'm going to run this. Let's check. You get the same table, but you get a chi-square value, degrees of freedom, as well as the p-value. And again, p-value is less than 0.05. And so we can consider this to be statistically significant. So we can say sex is associated with unsuccessful treatment outcome. Is this clear? How to examine categorical variables? Okay, yeah, good. So let's move on. There is one more thing which we have to understand here. We realize that there is an association now. But the next question is, okay, there seems to be an association, but what is the magnitude of that association? Okay, we have to give a measure of association. What are the measures of association or measures of effect? We have common ones, odds ratio, rate ratios, and relative risk. Since this is a cohort study and we have information on incidence of outcomes, so we will go for a relative risk in this case. Okay, and the command for relative risk is option RR. Option RR. Is this clear? So let me run this. You can see. Okay, so now you have got the chi-square, p-value, as well as relative risk with its 95% confidence interval. Is this clear? Is this clear? Okay, so 2.12. How do you interpret this 2.12? It means that the and I also want you to note one nice thing in this table. It is clearly telling you what is the exposure and what is the outcome. What's the exposure here? Male. That is the exposure, and outcome is unsuccessful outcome. So it clearly says that males have 2 times higher risk of unsuccessful outcome as compared to females. Is this clear? And one of the things I have to show you here, whenever you are using a relative risk, let me put a VL to show the values and labels. Okay, and you can see here it arranges itself in the descending order of values in both row as well as columns. Do you see this? So as intuitively you can think, if you want to examine certain associations, then you can code variables in such a way that the intended outcome will get a higher number and the intended exposure will get a higher number. If you ensure that, the table will arrange itself perfectly in the way you want. Is this clear, everyone? So this is a cohort study, and indeed we need only relative risk, but also in case control study situations we may go for odds ratios as the measure of association. I also want to show you in the same example, if I were to calculate an odds ratio, what will happen. So the option is option O. Option O. Let me run this. Okay, so now I've got relative risk as well as odds ratio, and you may note already that odds ratio is near to 3 while relative risk is near to 2. This is another important principle to note. Since the outcomes are not rare here, okay, odds ratios overestimate associations. So as far as possible, whenever it is possible to calculate a relative risk, like in a cohort study, always go for relative risk. Don't go for odds ratios because they overestimate associations. Whereas in cross-sectional or case control studies, probably you can go for odds ratios because there you don't get a measure of the incidence or risk. Is that clear, everyone? Okay. So let's go through some other examples before it becomes clear. So let's take another one. Is BMI associated with treatment outcome? Examine in 2 ways, continuous as well as categorical. Okay. So continuous means all we have to do is simply say means BMI. Is mean BMI different among those with the successful treatment outcome as compared to those with the unsuccessful treatment outcome? It's similar to what we did earlier. It's means BMI by outcome 2 and do a t-test. Let's run this, and you will see that those who had a successful treatment outcome, the mean BMI was 19, whereas unsuccessful it was 18. Okay, there appears to be some difference, and that difference, if you take the criteria of 0.05, is not statistically significant, but there appears to be something happening here. Okay, very clearly those who had an unsuccessful outcome had a low BMI at baseline as compared to those who had a successful outcome. Is this clear? Okay, now let's look at categorical way. I mean, this is the same as looking at the way we looked at the variable sex. All we have to do is first convert BMI into categories, into whatever categories you want. Maybe undernourished, less than 18.5, and normal, more than or equal to 18.5. And once you do those 2 categories, you can probably look at whether outcome is related to BMI as a categorical variable. So I will not do that now and leave it to you as an exercise. Let's look at some other variables. Is alcohol use associated with treatment outcome? Okay, is alcohol use associated with treatment outcome? Let's look at this. So how do we look at this? Tables, command, the outcome is outcome 2, and then the exposure variable is alk. Okay, alk. Okay, and then we want a row percentage, isn't it? Let's look at this just. Oh, there is a category called not recorded, isn't it? And I think it is coded as 9. Yes, so I put a VL and see that it is 9. So we have to exclude these 4 people from the analysis, because if we have to calculate relative risk or odds ratio, we need a 2 by 2 table. We need a 2 by 2 table. So I'm going to exclude this group not recorded. How do I exclude? I will say if alk not equal to 9. Run this now. Now I get only for the 2 people. And you can see here those who consumed alcohol, had 87, almost everyone had an unsuccessful outcome. Those who didn't consume, 30% had an unsuccessful outcome. Clearly there is a big difference. And now the next question is it statistically significant? So I do a chi-square test. And clearly P is equal to 0.0000. As expected, it is statistically significant. Okay. Now I want to find out a relative risk. So option RR. Okay. What does it tell? Again, you have to look at exposure. Exposure is not using alcohol and outcome is unsuccessful. It says RR is 0.35. Whenever RR is less than 1, it means it is a protective factor. Just because it has rearranged itself in descending order, because that is what happens in a table when you give relative risk. If you do not ask for a relative risk, then default order is ascending by values. Do you see this in the first table here? Whereas in the epidemiologic table, or whenever you ask for odds ratios and relative risk, it rearranges itself and the default is descending values. Is this clear? And you have to use one of the sort options to rearrange this correctly. Is that clear, everyone? Is that okay? Yeah? Okay. So let's try rearranging this. Okay. Now I have to tell you there are several options. And there are totally 6 sort options. One is option SA. SA is sort ascending. SD is sort descending. So if values are arranged in ascending order, then you do a SD if you want descending. But here in these 2 commands or in these 2 options, it will do for both row as well as column variables. It will do ascending for both row and column. Similarly, it will do descending for both row and columns. Okay. But if you want to change only one of the 2, only row column or only column or only row, then you have to go for other options. The options are SCA, sort column ascending, sort column descending, sort row ascending, and sort row descending. So these are the 6 sorting options. Now I have to inform you here a bug which is there in EpiData, that is sort ascending and sort descending, these 2 work perfectly fine. Whereas the other 4 options, they don't work as intended. Okay, this is a bug in EpiData. We have reported this to EpiData Association and they are working on it. But there is a workaround. If you use one of these 4 options, then it will certainly give you what you want. Okay, so you have to arrange the table accordingly. So here in the column it is fine, unsuccessful and successful, but only in the row heading we have to change. You see, yes has to go up and no has to come below. So we can actually try some of these options. So let me try, because it is descending, I will try only the ascending options. And I'm going to try first, let's say I try row ascending. Okay, let me try that. Row ascending did not work at all. So I will try a column ascending. Yes, now I have got this in the way I want, and you can clearly see relative risk is 2.84. That means the risk of unsuccessful outcome among those who consume alcohol is 3 times greater than as compared to those who don't consume alcohol. Is that clear? Is the interpretation clear, everyone? Okay, fine. So let's move on. So alcohol use is indeed associated with unsuccessful treatment outcome. So let me go to the next question. Next question is an interesting one. It is asking, in the association between alcohol use and treatment outcome, is sex a confounder? How do you say whether sex is a confounder or not? There are 3 criteria. One is, for any variable to be a confounder, it should be associated with the outcome. Second, it should be associated non-causally with the exposure. And then it should not come in the way between exposure and outcome. These are the 3 criteria, of which 2 we can easily test. Is sex an independently associated with the outcome? Yes, because we just checked that, isn't it? So if I run this again for you, you can already see that sex is in fact associated with unsuccessful outcome. So that fulfills one criteria to be a confounder. Is sex associated with alcohol use? Probably yes. Given our setting, alcohol is consumed mostly by males and rarely by females. But we can check it in our data set. So how do we check it? I'm going to say alcohol vis-a-vis sex, and then I'm going to say a row percentage. So as expected, if you see here, among females, none of them consumed alcohol, whereas among males, about 11.5% consume alcohol. So it is also associated. We can run a t-test if we want and exclude missing data here, and then you will get 0.0224. Very nicely here it's saying cell expected less than 5. So cells with an expected value less than 5, there is one cell. Okay, so if the expected cell value is less than 5 in any of the cells, then we do what is known as a Fisher's exact test instead of a chi-square test. Okay, Fisher's exact test, and the way to do it is option EX. I can run it. Now I get Fisher's exact test. P is equal to 0.0245. So clearly sex is associated with alcohol use as well. So it's associated with outcome, it's associated with exposure. So it's indeed a confounder. So how do you adjust for the confounding effect of sex and find out the independent effect of alcohol on treatment outcome? Is this very clear? Yeah, I want to find out the independent effect of alcohol on treatment outcome after adjusting for the effect of sex. How do you do that? One way which is possible in EpiData is to do a stratified analysis. I'm going to examine the association between alcohol use and treatment outcome stratified by sex. Is that clear? So let me go and pick my main line. This is tables outcome to alcohol. Want a row percentage, t-test, chi-square, relative risk, and all of this. Okay. Now the way to get a stratified analysis is very simple. All you have to do is go after your exposure variable, put the stratifying variable. Okay, so tables, this is the outcome variable, the key exposure variable you are interested, and then the variable you want to adjust for. And what you get is a stratum specific. Let's run it and look at the output. Great, I've got an output. Let's carefully look at this. I've got 4 tables in all. The first table is the usual one, unstratified table. Can you see here the bottom? Unstratified table. Exposure is alcohol use and outcome is unsuccessful outcome, 2.84. This is the crude RR or unadjusted relative risk. Then we get stratum specific information. So now it is examining alcohol use versus outcome among females. And as you can see, there was nobody who consumed alcohol among females. So this stratum is non-informative. We can't say anything from here. Whereas among males, you can see clearly relative risk now is 2.54. Okay, there is a association between alcohol use among males. Okay, and then look at a summary. This is a nice summary. You have a crude relative risk which is 2.84, adjusted relative risk. This is the Mantel-Hensel's adjusted relative risk. It is 2.54. Okay, and then you also get stratum specific relative risks. Okay, so ignore these for a while because it's not very informative. How to look for confounding? All you have to do is look if there is a difference between crude relative risk and adjusted relative risk. And whatever difference is there, that is due to the confounding effect of the variable that we are stratifying. Is that clear? Okay. So here we are not looking at whether this difference is statistically significant or not. No, that is not the question. Any difference between crude and adjusted is due to the confounding effect of the stratifying variable. But prior to that, you must always examine the stratum specific relative risks, because if the stratum specific relative risks are very different, then there could be a possibility of interaction or effect modification. We are not going to all these terms in detail. Probably we had discussed briefly in our module 1. But the way we can also look for interaction is if you look at stratum specific relative risks and they are very different from each other, then probably you can think of a effect modification here. And in such cases, it is recommended that you present the stratum specific relative risk rather than giving a adjusted one. Is that clear? Because if you do an adjustment, the presence of interaction will not be documented. Okay, great. So let's go back. So we finished that. So this in essence is we've covered most of the things in inferential statistics. Clear? Continuous variables, means, difference in means. We've looked at unpaired t-test, paired t-test, Kruskal-Wallis test. Okay. We've also looked at categorical variables, chi-square test, Fisher's exact test, how to calculate relative risks, odds ratios, 95% confidence intervals. We've looked at sorting options, and also we've looked at stratified analysis along with calculation of Mantel-Hensel's relative risk. Is that clear? Okay. Thank you very much.